pleasure to introduce Professor Spencer Quiel. He's an associate professor at Lehigh University. And Spencer, thank you, and the floor is yours.
No, thank you, Thomas. And thank you again for the opportunity to present in this forum. This is really a great opportunity. And I'm a longtime SAFIR user. I began using it in 2004 when I first started my graduate program at Princeton with Maria Garlock as my supervisor. And literally showed up on my first day and there were manuals waiting on my desk. And it was like, here it is. And I was like, what is this? And that began a very long process that I'm very grateful for to this day. And I've really enjoyed using this program and really seeing it evolve and using it for things such as this. So I think I'll go ahead. So today I'll just be giving an overview of a project that we just recently completed for PennDOT, looking at prestressed concrete bulb T girders. PennDOT has been a really good partner with bridge fire related projects. They had some questions preceding the I-95 collapse that happened in Philadelphia, leading up to, how do they manage risk of their bridge structures, what things are vulnerable, and also what potential protection methods or mitigation is available to these structures. So they've been very proactive, and I've been really, in interviews that I've given on this topic, I've been always trying to make a point and throwing PennDOT, some credit here for really being ahead of the curve and being aware of some of these hazards and trying to get out in front of it. And I'd like to also acknowledge my collaborators on this work, Professor Clay Naito, my co-PI on this project, and also Zeta Zhu, who was the postdoctoral researcher and really just the driving force behind the implementation of all this in SAFIR. So without any further ado, so this is me just really quick. I'm a longtime SAFIR user. Structural fire engineering is what I began my dissertation work in, and it continued through my professional practice, then to my time at Lehigh. I also do some protective design engineering, as well as structural resilience. A lot of using things like SAFIR and other softwares and interfacing it with MATLAB to do larger scale or probabilistic analyses. And also risk assessment for bridge networks, tunnels, buildings. So it's a pretty wide range of types of projects, but within these general topic areas. So the research tasks that I'll be presenting today that were funded by the Pennsylvania Department of Transportation is going to be basically rolled out in two phases. One thing they've been concerned with is not only vehicle fires, but also materials that are stored underneath of bridges. So the DOTs happen to own a lot of space underneath of bridges that then they lease or rent, and then they have materials, some of which can be combustible, which are stored underneath. And so one of the cases they've been concerned with was the I-85 fire in Atlanta, which occurred in 2017, in which bulb T pre-stressed concrete girders failed after just a little over an hour. And so to use that as a baseline, somewhat of a forensic validation opportunity to then say, can we get a model using SAFIR as the driver that then we can assess a different or similarly designed but slightly different bulb T cross section that PennDOT uses commonly for fire assessment. So this is really where we began with this project with these two tasks, and then beginning with the Atlanta I-85 bridge fire. So again, this was a bulb T girder system that we basically passed through these structural fire engineering phases: fire load quantification to thermal analysis, in which we also included Spalling. So I saw Nagar's excellent presentation just before this and incorporating Spalling in tunnels. So we did this a similar approach where we were putting a Spalling consideration onto bulb Ts, so some complex beam-related geometry, to see if we can get then structural predictions, which were close to what happened in the field. And then looking also at flexure primarily, but also at shear to a lesser extent, just to make sure that that wasn't a controlling failure mode. So some basic information about this bridge: the span that collapsed was the what's called 30 northbound, had a 23-foot clearance from the ground. It was approximately a 92-foot span. There were other spans that were also affected but did not collapse, so they were also replaced at the time of the reconstruction. So the failure time was approximately 1 hour and 9 minutes for this event. So we were able to get all this information from the Georgia DOT, which is also another partner on this project. This is a part of a report that we submitted to PennDOT and is also in a journal publication with this forthcoming. It's in the draft phase. But looking at this profile and the girders that were there on the 30 northbound span, the cross-section had an arrangement of pre-stressed strands and also mild reinforcement in addition to a composite deck. And then also some of those strands were harped. There's also the design drawings and the shop drawings, which had some differences. So the one I'm going to highlight here is the shop drawings, what was actually installed in the field. And so there is a collection of those strands, which you can see down here in the bottom for the shop drawings, that at midspan, they're in the bottom of the bulb, but going toward the supports, they are harped and the center of gravity is moved all the way up, really just right into the top flange. Our SAFIR models consider all of this. So we're able to, if for each element going out toward the supports from the middle, we do change the elevation of that one grouping of strands so that we can have that harping profile and really mimic the exact structural setup of the bridge. And so we had the details, how many strands, what sizing they were, what the overall center of gravity was, and the material properties. So with all of that, we laid out the cross sections. But before we proceed any further, we had to quantify the fire that we would put on that cross section. The thing that made this fire severe was there was high density polyethylene conduit that was stored underneath. And there was a lot of it stored underneath. It's not necessarily the best material to store under a bridge. So we looked at the layout of the spools. This is available in the Federal Highway and NTSB reports. But looking at some of the worst cases, and they do go the full span underneath some of the girders, we did a little bit of a forensic analysis looking at the mass of high-density polyethylene per spool, how many reels there were, total mass, total area, heat of combustion, and we came up with an assessment of about 136 megawatts, which would be slightly smaller than a heavy goods vehicle per the NFPA 502 specification, which would be at about 150. So, and the burning time, the whole total time of combustion for this much fuel for solids as well would have been a little bit over 2 hours. So when it failed, there wasn't enough fuel to keep going. So that was really something that was going to push it all the way until you got to a failure condition if it was under that time. So the one thing that we tried to do is simplify it down, at least to some extent. And we do show some more detailed fire application that's localized later in this presentation. But for the forensic analysis, the ASTM E1529 curve, and we use the upper bound, so the 166 kilowatts per meter squared, is roughly intended to represent an engulfment of a hydrocarbon fire. And so looking at the worst case girder, we calculated flame heights based on some estimates on the 136 megawatt heat release rate. The girders were engulfed by this, and the eyewitness accounts verify that. And so we used the heat flux that corresponded to 1529 as a means for putting a relatively uniform, what we approximated as uniform heat flux over the length and over also the perimeter, the heated perimeter of the girders, and then proceeded with analysis with Spalling incorporated, got the thermal results with the cross-section that reduces, and then feed it to structural analysis. And so, and you can see here in the upper right with each of these cross-sections, the harp strands, which do move. And in the web, also as you have Spalling, they become more vulnerable because they're in a more slender piece of the section. And so if you look at the cross-section, the way we discretized it, using some of the tools in GID, we've also used some of the newest tools that have been released by Thomas and Jean-Marc and their team, trying to discretize as heavily as we can, as appropriately as we can around the edges where we can spall these fibers off, and then have the strands under that, with then the representation of the heat flow going to them. We do have the Spalling halt at the mild steel vertical perimeter reinforcement. That's also per observations and testing. But the entire perimeter is heated, and it's assumed an engulfed scenario. And we do have the pre-stressed concrete, the non-pre-stressed. We do put the initial pre-stressing into the strands and let it react for a couple of time steps so it gets that appropriate sectional equilibrium for the pre-stressing. So there is an initialization that we do when we begin the structural analysis for this as well. And the whole process has worked very, very well in terms of getting the amount of pre-stressing that we would expect just based on initial hand calculations, and also getting the initial conditions for what happens next. which is a progression of thermal spalling. So similar to the previous presentation, we also use a MATLAB SAFIR interactive algorithm to do restarts of the analysis. And this is really a simplified representation of just a single panel, 1D heat flow, looking at fibers. And the bulb T presents a lot more complications in terms of discretization and then spalling really perpendicular to any surface, which we're able to do with the algorithms that Zeta has really pioneered. Based on experimentation that we did in our lab, looking at the spalling of normal weight concrete panels, we essentially are letting the concrete heat when the surface gets up to 450 Celsius. At that point, the test that we had run would spall to a depth at which the temperature was approximately 150. So when it gets to 450 at the perimeter, then from that point to the 150 depth, that chunk is gone. That gets removed. We then move the fire frontier forward and then restart the thermal analysis. And from that point, and then continue until you get another condition that then continues. You spall chunks away until the rebar, the mild vertical steel, we get to that layer. And then again, per experimentation, what we've seen, we stop and then we keep heating. And then that total thermal file, so we do that iteratively with MATLAB, feeding them back and forth and doing restarts. And we take that thermal file and feed it to the structural analysis. And so that then becomes the basis for what we see flexurally and then doing our evaluations. So again, exposing this to the 166 kilowatts per meter squared for fire engulfment, for hydrocarbon fire engulfment. We do the iterative MATLAB algorithm to then basically peel the layers away, but doing it in chunks from it, basically spalling away layers done differently at each surface. So the web will heat up a little bit faster just because of its, it has less concrete than the bulb. Then you can basically do this differentially in different sections, and you can see a little bit of a representation here at the transition from the web to the top flange about how these layers are peeled away with the discretization. One of the challenges is when you make bends in the discretization and getting it to spall uniformly. We do see in this representation a little bit of jaggedness with how that peels away. We did do some smoothing algorithms in our geometry, just in the mesh sizing, just to try and mitigate some of this. So this has since been improved a little bit. But at those thick layers where you make transitions, some of the testing also shows transitions in depth of spalling from the flat to the transitional or curved or angled surfaces. So not a terrible approximation. We've done some numerical things to try and smooth that out, but we can get this progressive nature in basically chunk removal of the spalling as it presents itself down to the mild steel reinforcement to get the reduced cross section and to get how the section heats up. And so the concrete cover reduction has been it's really progressed nicely with not only this analysis but also some other projects that we've done recently. Then we can couple those thermal results with our thermo-structural materials. So the reinforcement, strand steel, and also concrete per Euro Code 2. We have our mechanical loads, which are accounting for the wearing surfaces, the self weight of the bridge, and looking at we do incorporate just a uniform live lane load, even though most of the live loads are gone by the time we get there. So we use a combination of 1 times dead plus 0.3 times that, just a very small live load, because we're assuming no large trucks are there. There's also a 1.1 dead load case we've done. So we do consider a couple different loading cases, totally eliminating the live load or having a little bit. But all of them give relatively comparable answers in terms of survivability, where when we let this model run, again with the harp strands and the section reduction, we see the moment capacity and the kinking of the fiber beam elements occurring not on center. It occurs off center at approximately 1/3 of the span from one side, which actually incorporates with the deck kink that you see in the field observations. So where the moment capacity is being reached versus where the damage is presenting itself, and also the failure occurring and you get runaway flexure at 1 hour and 4 minutes versus 1 hour and 9 minutes for the actual event. So what we're able to obtain with the interactive spalling, with all these, with this modeling approach versus with the actual event, was we were very encouraged by, using this as somewhat of a forensic validation opportunity and looking at the model as being very, very useful. So some of the further investigation we did to kind of peel away some of the layers for verification is we were examining compressive stresses at the top fibers of the cross section at different elements along the length, midspan, working your way over, and looking at element 30. So again, that kind of 1/3 or 0.35 length span from the one end. Yeah, that's where it's spiking. It's peaking, and you're getting most of the compressive forces as you begin to get deflectoral runaway. Looking at moment capacity, so the temperature in every fiber, and doing the summation for every time step, we then can track the demand on each segment versus capacity in time and verify again at element 30. That's where they strike. So that's where the two curves are basically running into each other. And that's indicating, yes, that should be where the flexural kink is happening. You get some hinging in the fiber beam model, and it basically begins the onset. This is a simply supported assumption for this particular girder. It begins the onset of flexural runaway. So again, confirmation of the fact that the section mechanics are making sense in terms of what we see presented in the overall fiber beam model, again, because of the harp strands. So we have these vulnerabilities as those strands are harped to try and spread out the flexural resistance according to the moment diagram. We see some of the vulnerabilities be off-center for a uniform fire application. So some really interesting things that we can note about how these things work. And again, plotting out the demand versus the capacities on time. So 0, 30, and then when it fails at 64 minutes. And again, seeing where we crash. We can use these lines to determine where these points of failure are going to be from a moment capacity standpoint. And again, that it matches up relatively well with what we observed in the field. There's also shear checks. Now, this is not a solid element model, and so it's not doing the shear check internally, but we can take the cross-sectional data and using the AASHTO LRFD specifications, their equations, which are going to be, we're basically trying to take that as lower bound of an approximation as we can. This was done in consultation with PennDOT to say, what is the overall temperature profile through the vertical section, and then looking at the steel, how it heats up as well, how the concrete has heated up, and then trying to come up with what is the overall shear capacity for the section. And that shear capacity is really a very conservative calculation for time, is being met just after about 5 to 10 minutes after when you would get to the flexural, getting flexural capacity. This is a very interesting area that I think really needs more research, and that we are pursuing a little bit more of. But looking at shear mechanics in really any types of long-spanning structures when you have thermal effects introduced. So this is definitely something we look forward to seeing more of in the future. So really just a really quick summary of what was phase one. Phase two will be quick. I want to try and leave some time for questions here. But the simulations in SAFIR and the way we're able to couple MATLAB and Spalling with the section mechanics really did a fantastic job of helping us capture the failure time of the event, failure location of what was to be expected, looking at the flexural moments, and also enabling a very conservative shear calculation, and then to spring forward to what PennDOT wanted evaluated, which was a BT72 section. Very similar span. They gave us a prototype. It's 90 feet, 90-foot span, 6 feet deep. So this particular bulb T section was a little bit thicker in the web. However, some interesting things to note is the vertical steel was outboard of the longitudinal steel that was in the web. The Atlanta section, those vertical bars were inboard. So they were actually a little bit further into the web stem. So we made those modifications. We have the strand profile, different spacing and different loading. But again, applying a lot of these same concepts, we began with the E1529 heat fluxes. We would continue it until it failed, doing it uniformly across this girder. And this one was a straight strand girder. So this one did not have the harping. But then we would do cutoffs. We would stop E1529 after 30 minutes, 60 minutes, 90 minutes, and see where it would recover. So if you were able to get the fire under control after that period of time, what would be your residual deflection? And so looking at those residuals, we've worked with PennDOT and coming up with a damage classification system, going from superficial, where it's essentially very small amount of damage, maybe requiring a little bit of repair, but you might be able to reopen it. Moderate, which is going to require possible replacement, more repair. Heavy, you're definitely looking at replacement. To hazardous, you're looking at collapse. And so coming up with this tiered system based on maximum and residual displacements in consultation with PennDOT staff, we then built from this just using the 1529 and then mapping each of those residuals. If you cut the fire off, what do they mean? Where do they place you in terms of being able to reopen or operate or replace or repair the bridge? To then looking at specific fire scenarios. So this is some of the last things I have to show, where you have what we call the modified discretized solid flame model. This is another thing that we've developed in our research group, again, led by Zeta Zhu, and looking at solid flame elements with smoke cones that are on top that then can give off heat flux to structural targets, and also enables you to do engulfment of structural targets for fire that's underneath. So these smoke cone will essentially smear, it will spread out, the fire will then directly impinge upon the structure. And then with this, so if you have a tanker truck fire at 300 megawatts, you get flame heights, you have a footprint size, you then can smash that solid shape underneath the bridge, it will spread out, you'll have attenuating heat flux profiles on some kind of geometry, just like this, where you then have heat fluxes over discretized elements, then you can map into SAFIR onto whatever geometry you want, using a time history for the heat release rate. So this is a localized fire approach. We looked at a couple different scenarios for multiple cars, buses, heavy goods vehicles. We didn't do the tanker just because that wasn't in the scope for what PennDOT was looking at for this particular project. And we did mid-span and quarter span, so that 1 and 2 for this particular bridge. Got all the heat flux profiles using our MATLAB-based MDSF software, in addition to the 1529, and did some comparisons. So again, being able to present localized fire exposure, and you then continue that exposure, see where it fails, and then in timing, if you can put that fire out or if it burns out, what is your residual? So 150 megawatts at a very low clearance, 15 feet, then going all the way up to 45 feet, and looking at how you change the exposure and the intensity and the damage. So with this, we were able to produce, PennDOT, has really been a fan of the, color-coded damage classification tables that they can use to make decisions. So SAFIR, in terms of doing this iteratively for different scenarios, using, again, the SPAL model, all the section mechanics that we had described previously, to come up with these design tools or maps. And it's been expanding from here. This is something that is definitely a work in progress, not only for these types of structures, but for others. But SAFIR, just really, the thing in red is that it's been enabling structural fire evaluation for parametric performance, both under standard and natural fire. Going back to standard fires has been important for them, because when they go to buy product or to make specification, they want to know how it's going to perform in actual fire, but they have to tell their vendors what they want. And that being able to speak that from natural fire to standard fire language has been tremendously helpful, because their vendors know standard fire specifications. They know an hourly rating. So allowing them to translate between the two with SAFIR has been tremendously helpful. And I'd be glad to take any questions about any aspects of the work here. So thank you very much for the opportunity.
Thank you very much, Spencer, and thank you for the fantastic presentation. There's been a lot of interest and question in the chat box on this, so I'll go through a few now. Jean-Marc asked, so you mentioned the incident heat or the heat flux of 166 kilowatt per square meter at the beginning. And so the question is whether you treated that as an incident heat flux or net heat flux. And so technically in SAFIR, whether you use the flux boundary conditions together with a frontier to re-radiate to the far field. Yes,
yeah, we had so essentially the F20 on that surface in addition to the heat flux. So yeah, per the manual and the recommendations for how you would apply heat flux, we followed all of that. And also we would do temperature-based boundary conditions, because that specification also has the temperature application as equivalent. We'd always do both of them just to make sure. It's always something I always start my students with, is that we need to do both to make sure that your heat flux is doing the same thing as just a pure temperature boundary condition if there's an equivalent. So we do that quite often when we're dealing with the 1529.
Thank you. A question from Ruben. When you described your Spalling, iterative computation. Do you specify a predefined limit to the spalling depth?
Yes. So we only go to where the vertical steel is, because with a lot of the testing, in addition to some of our own on doing panel tests that had bar reinforcement, is that you could spall all the way through the cover, and then you would eventually have stoppage when you start to see the vertical steel. The I-95 event, which recently happened in Philly, it actually, I was on site, and the piers, the abutment walls where the fire was most severe, you could see the reinforcement. It was all spalled away, but it hadn't progressed actually any further than that. It was visual confirmation in a way of a lot of the testing that you can get spalling to at least arrest somewhat. It won't keep going once you get to that reinforcement layer. And it actually kind of had confused some of the engineers on site, suggesting that why didn't it go beyond this point? I actually ended up sending them a couple of papers by others, just saying that this has been seen before.
Interesting. Thanks for sharing that. There was a question. So you spent a little bit of time explaining the position of the failure, right? The section that is in the end that reaches the failure in the first beam that you showed. Can you explain a little bit more? So why is this in this element 30 not at midspan? And well, yeah, if you could elaborate a little bit on that.
No, absolutely. So when the strands are harped, and so that there's a bundle of about 5 strands, a column of them, which will then in every element going toward the end is pulled further and further and further up. When they get into the web, they're more easily heated. And so when you're harping them, you're basically spreading out the moment capacity. You're making it differentially to kind of follow the moment diagram. The strands end up helping a little bit in the web once you get to the ends in terms of shear resistance. And so when you have them heating a little bit more aggressively, and also the moment capacity just by default is a little bit lower at that section anyway, and you had uniform heating along the length, that particular section represents the critical point. And so we were trying to just allow what was going to happen, and then be able to monitor how that capacity was being reached. And that's why we did the section analysis at each of those junctions.
I see. So you could see that vulnerability, at least partly by looking at the thermal analysis result. If you plot the temperature in the strands along the lengths, it was the hottest. Oh, I mean, it's a combination with the mechanical response, but it gets hotter there than at midspan.
Right. Yeah. So you could see the combination. You might have some areas a little bit further down the span toward the support where the strands would get a little bit hotter even. But the thing is, the moment is a little bit lower out there. So you could probably do at least enough of these analyses for pre-screening to determine what temperatures you're looking for. And also then the second section that we looked at for PennDOT was just straight strand. So all that went away, and we ended up having basically the section capacity was reached at midspan for those particular sections. But by doing the harping, we were able to, with thermal plus structural, monitor for where that would occur. And then again, looking at the field observation for where you had the huge crack in the deck to see where, what would be the first indication of where it actually failed.
Thank you. And maybe a last question from Jean-Marc about the solid flame model. The question is whether you use the procedure LOCAFI, but I know your group has been developing lots of solid flame models as well. So maybe you can comment a little bit more on that, what you've done and how you couple with SAFIR.
Right. So the solid flame models we've developed from some of our research going all the way back to the things we were doing with the MacArthur Maze fire. And we've had a series of publications where we've been iterating on it and, adapting it to different types of scenarios. So all that we've developed, I had originally the very, very beginnings of it developed when I was at Hinman Consulting Engineers back in 2012, 2013. And then Zeta has really been the one, driving it forward in his dissertation and beyond during his time at Lehigh. And, so that's a MATLAB algorithm that we have used in a number of applications, notably a lot of them for PennDOT. We've also adapted it for tunnels to include convective effects. And in some cases, we've also, for our tunnel work where we've used CFAST as an additional tool, we've used, FDS to basically do confirmations and also test data. So these tools they're relatively fast running. They are discretized. They do require algorithms to do them, but definitely less computationally heavy than something like CFD, even though we have used CFD to basically as verification in past projects.
Thank you. And so just briefly, but how do you interface the outputs of that with SAFIR?
So we have Zeta has several MATLAB algorithms where we do the mapping for what the heat fluxes would be at certain locations along the discretization of the 3D model that's in MATLAB, and then mapping that to the SAFIR model. So I mean, we're almost always trying to use the same discretizations for what our fiber beam elements, or in some cases shell elements, are going to be, so that we can get the distributions and the contours to be consistent.
Thank you very much again, Spencer. It's much appreciated. Thanks for the presentation and for the answers. Thank you.
No, thank you very much.